next speaker is Brian Baade. Brian worked as a practicing painter and illustrator after graduating from the School of the Art Institute of Chicago before devoting his career to paintings conservation. He's a graduate of the Winterthur University of Delaware program in art conservation and worked in several places, including Château Parentignan in France, Amsterdam, and at the Yale University Art Gallery, prior to his current position as an assistant professor at the University of Delaware, where he teaches courses in the materials and techniques of Western art in painting and technical art history. He has two co-authors to his paper, Christine de Cataldi and Jennifer Mass, and he's gonna talk about what are our true detection limits. Hopefully he'll have answers from us.
So thank you, and thank you very much for the organizers and having me come here and represent our research. Let's see if we get everything worked out here. Okay. So yes, what are our true detection limits? The use of historically representative paint media to evaluate the sensitivity of XRF analysis, including a comparison between laboratory-based and handheld XRF instruments. Wow, that's huge. And like most of these conferences and people that speak at these conferences, you make up this title and that abstract when you started the research. And so what often happens, though, while you're actually doing the research is you wish that somehow you could start and change that name to initial steps into determining what our true detection limits are. But hopefully I'll be able to give you some answers, at least based on the research in which we did, based on the materials that we created and the analytical tools that we used. So, artist materials versus current XRF technology. The previous talk was really wonderful to see this evolution of XRF technology. I was also quite blown away about the ability to see that aluminum in ultramarine without a vacuum, because as you will see later, I was not able to do so. What we're going to do, though, is just to check, using the instruments that we had at hand, how effective is our current instrumentation at detecting traditional dryers, so those leads, manganese, even zincs, cobalts that are used to catalyze oxidation of oil paint films. And those red lakes and their associated mordants, the very common ones, the aluminum, tin, calcium. And then finally, Lapis lazuli obtained from historically appropriate sources, so actual lapis from Afghanistan made into a pigment and then refined or not refined, as the case might be. So the instruments that we worked with were the instruments that we have at SRAL, the SRAL that's at Winterthur University that Jennifer Mass, who is also a co-author on this paper, heads, as you heard from her earlier. So we had the Artex Micro XRF unit, open architecture system. We can basically see potassium to uranium. Analysis area is 70 to 100 microns or so. We did have the ability to capture with and without a helium purge, so we were able to go down, or at least in theory, able to go down and see those elements with the atomic weight below that of potassium. Our parameters that we used on all of these were 600 microamps of current, 50 kV, and then a full 600 seconds live time. We wanted to capture everything we were going to capture, so that full 10 minutes allowed me to work on other things at the same time. I think I passed something, yes, here. So and then we compared that, or at least in some instances, we compared that with the Brooker handheld instrument, which we had use of a vacuum, so we were once again able to theoretically see elements below potassium. Had slightly different parameters. These are on the board here. When we were analyzing things below potassium, we took that filter out, took out that titanium aluminum filter, and changed our parameters slightly, and then used the vacuum unit. So, the paintouts and dryers that I made and then we analyzed were applied to a mylar substrate. Thankfully, wonderfully, we were lent the thin film standards from the GCI so that we could create calibration curves and really to see, can we see how much we can see and where does it fall and how can we compare one standard or one of our materials versus another. Kristen and I began to devise this idea for the research when thinking about the possible effect of lead and other dryers on the XRF analysis of paintings. During our analysis of this David Teniers, lead peaks appeared to remain the same, moving from one color of paint to another. Obviously, these peaks could originate with lower lead layers, but it's my understanding that we see attenuated lines when this is the case. In this instance, the peak pattern did not change even when we moved from an area that was quite dark to an area of a bright white highlight. This made us wonder if, even not in this instance, could it be the appearance of a lead or the instance of a lead dryer causing one paint to appear to have a much higher lead count than even you would expect, and that to simulate that of the lead white layer. So moving from there, we began to wonder about the influence of other dryers. What about cobalt dryers? One of our students was examining this Robert Miner on the right-hand side, which is owned by the University of Delaware, and then came here to the American Art Museum and examined their great Silas at Night by Robert Miner. He's a painter associated with the Barbizon School. She analyzed these with XRF and SEM and seemed to get hits for cobalt throughout paint layers in areas that seemed to have very little reason for there to be cobalt in it. In SEM, it seemed to be throughout the cross-section in areas that we could find no cobalt green, cobalt blue, or cobalt violet, as we were hearing talked about earlier today. Now, first of all, Kelsey Wingle, who's working on this research, came and asked me, and I said, I'll do a little bit of research about cobalt dryers because I've seen very little reference to cobalt dryers before the 20th century. Most of the use of cobalt salts, and especially the patents for cobalt dryers in the United States, it's cobalt resonates in 1916, and it's really not to the 30s when we get linolates and then finally naphthanates. So, with a date of 1890s, it doesn't seem very likely. However, doing some more research, it looks like there are actually references to cobalt linolate as early as 1854, and I have those references if anyone wants to see them, and that there is a translation of a publication that's published in Philadelphia in 1974 that mentions the use of cobalt linolate. So maybe cobalt dryers are a possibility. The idea of the influence of cobalt on XRF and SEM became even more intriguing. So we replicated and created these 5 dryers and or paint mediums that would accelerate the drying rate of paint. In fact, I made a 6th one. I mentioned earlier that zinc. I made a zinc sulfate pale drying oil based on a 19th century recipe that seemed to follow everything in the recipe. And the issue was when we actually put out a dried film of that, I could find absolutely no zinc in it. So rather than to go through all of the questions, is zinc even incorporated in this? Certainly we should be able to see it. We just pulled that right out of the study. Before I move on, though, I'm going to tell you about how we made these drying oils, and you're going to say, oh my God, you're heating linseed oil up that high. We did do all of this a number of years ago, in fact, in a fume hood that was originally made for melting lead, for melting metals, and it has a very strong fume extraction, and it would set up the hot plate directly in front of that, and all of those acrid fumes would be going up that chute. So the first recipe to talk about, this is a coarse drying oil. This is mentioned in Dossi in actually the 18th century. It involves a lot of materials. Cold pressed linseed oil, as we'd expect. This has gum arabic, litharge, so lead monoxide, lead acetate, deadly lead acetate, some of that zinc sulfate, and then some raw umber. So we've got definitely a couple lead products in there, compounds. We have iron manganate, and so we have manganese dryers and lead dryers. Can we see those? It took to about 250 degrees Celsius to actually incorporate in there. A leaded drying oil. This is going to be used throughout the 18th, 19th century, throughout the 19th century without a doubt. And use the recipe, really kind of a combination of lots of recipes because the amount of litharge added in these drying oils can be anywhere from 6 parts to 10 parts oil to 1 to 20. And went to a kind of a middle ground of about 1.5 to 10. That's weight volume, about 230 degrees. Now before we can say, I know exactly how much lead or manganese or anything else is in one of these drying oils, we have to remember the process of making a drying oil involves melting all of this, having it incorporate into the linseed oil, and then letting it sit for a period of time. And these are the jars after 2 weeks of letting that coarse drying oil, after I've decanted it, all of this material is left at the bottom. This is that leaded oil with this material left at the bottom. But it really doesn't even stop there. Most of the recipes in the 19th century tell you to keep it for very long periods of time. Well, that lead is constantly being precipitated out to the point where it stops. It still is just as siccative, but it clears up over time, meaning it's a much more limpid and clear oil, but there's going to be less lead in it over time. So for me to tell you exactly how much lead is in the final product is going to be difficult. Difficult without much further greater instrumentation. I can tell you what I used to make the drying oil. Another interesting material is something called gumption. This is a 19th century painting medium. It's a mixture of lead acetate, so this white powder you see here is lead acetate. This is mastic resin. This is linseed oil. Those three materials are mulled up together, preferably with some really thick gloves, until you get it to the point where you've powdered that mastic. That then creates a gel, which you can see down here, painter's butter, that's very unctuous, has a wonderful buttery quality to it, and it was loved in the 19th century. This was the light version of McGilp. So if you were worried that McGilp, which I'll talk about next, is going to darken your lead whites, this is one you could use in place. It's used throughout the 19th century, sold by most of the colormen in England, available in the United States because we used a lot of British sources. And then there's the infamous McGilp, which you probably heard about, that mixture of a leaded oil with a mastic varnish. You see here the mastic varnish. The leaded oil has been poured in there but not mixed. Shake that up and you'll see what happens here. It turns into a soft jelly. This is thixotropic. It dries overnight or within a day or two when you're oil painting. This is loved. This is the same thing that was used for faux finishing, or at least for decorative painting in the 18th century. And then Jacques Meriget in the 20th century suddenly found that it was the secret of Rubens. Probably not. And then finally, the one material that I didn't make was the cobalt dryer. So this is cobalt naphthenate. Cobalt salts dissolved right into a solvent. Previous to this was cobalt linolate. Cobalt salts dissolved into oil. And then cobalt resinate. Cobalt salts incorporated with a resin, probably rosin. I don't have an exact formula, although we did run this on the XRF and could say how much cobalt was in that film, but of course that doesn't take into account how much of that solvent evaporated. This came from a proprietary source, as you can see, Grumbacher. People would often say in these artist handbooks, you know, add about a drop to a nut of paint. And I think for the most part a nut meant a chestnut size. I don't think a walnut or hazelnut, but usually about the size, and this is about what I stayed with, about the size of a chestnut. Other authors said things as simple as, please do not add more than 2% because it really could degrade your paint films. Here's a sample calibration curve based on those thin film standards that we had. And we did get a line of best fit that we put in there. The values were obtained by calculating the net area under the primary peaks, any contributing elements from the mylar substrate, and it did turn out that there was some calcium in the mylar substrate, and if I were to redo this, I probably would use a different film for that. But we subtracted that out. And the values obtained were used to estimate the concentration of the related elements in the paint outs. Let me get some water here. And this won't be shown later on, but this is always going to be the same. It's always going to be the X-ray counts here on the left side and then the concentration on the bottom. So the X-ray XRF analysis of the lead dryers. We did find these lead dryers were very easy to see. They were easy to see in paint. And we actually really got very similar results using both the Artex and the handheld. Interesting thing that we saw, though, is paints that had absolutely no lead pigment in them, but that were pigment ground in a leaded oil, showed a very strong peak for lead. This makes me wonder how many times someone has assumed a paint had a little bit of lead white mixed in it, but we can't see it in the cross-section, but it kind of probably has to be because we're seeing a lead peak there. Here's the lead calibration curve on the bottom where all of the paints containing lead were detectable. McGilp had the lowest amount, and Gumption by far the highest, and we'll see that in the next slide. First of all, though, I do want to talk about that coarse drying oil. So that oil was the one that had lead, it had manganese in it, and had some other things that probably didn't contribute to a great extent to drying. We were able to see that manganese as well, even though it was a very small component in there. The gumption, which is that paint medium made of grinding the mastic resin with the lead acetate, is way outside of our calibration curve. I mean, it is so far outside out here, it's really difficult to say exactly how much we have. I mean, that makes sense in a way because that lead acetate is approximately a third to more of the whole composition of the McGilp.
The XRF analysis of the cobalt dryers, despite being added in those relatively small amounts that drop to a nut of paint, the cobalt was readily observed in all reference spectra. The relative amount was relatively low. We're talking 40 micrograms per centimeter squared, lower part of the calibration curve, but seen every time. And also that we had similar results obtained with both the Artex and the handheld. It's heavy metal pigment. That's not really surprising. This is what I need to read. So, questions have arisen relating to XRF sensitivity to mordants, such as aluminum, calcium, tin, and others. How much of these materials must be present in the surface before the instrument can begin to detect them? While aluminum is certainly perhaps one of the more challenging metals or mordants to detect, calcium was commonly used, as was tin. And this doesn't even get into the incredibly complicated situation of lakes in the 19th century. It's not something that's talked a lot about, but there are all sorts of metallic salts used to precipitate lakes in the 19th century to create that vast palette of madders and cochineals and other lakes that are available in the 19th century. If you were to look at a Winsor Newton paint catalog in the mid-19th century and the array of madders, you may see dozens of them that range all the way from a deep dark brown, which could be just a burnt matter, it could be also precipitated with iron or copper, to some really brilliant tin containing to some that involve lead. And Kramer Pigments has replicated a lot of madder lakes, and in corresponding with them, it turns out a lot of those, they're using lead and copper salts in them as well. So it's another thing we should probably be thinking about when we're seeing a red layer that appears to be a lake and seeing heavier metal elements that we're not really expecting. So this was an interesting article, and I don't have everything on here. You can see the reference down here. And Chris and I really enjoyed reading this article, as the group did an excellent job of preparing standards to simulate Mantegna's paint layers. The presence of calcium in blue paint was concluded to be Lapis, and that makes perfect sense. However, the calcium seen in the red area actually increases as compared to other areas. So the understanding that maybe this calcium comes from the ground surprised me. I may just not be understanding. It is, however, difficult to know whether there's actually calcium coming from a calcium-containing red lake. And the authors may very well have known this and taken this into account. It's just not something that I gleaned from the article. I just think I want to put it on here just so that we think about that. Calcium-containing red lakes are very common. Brazil's and cochineal lakes very often had calcium to make a less expensive red lake, especially things like cochineal. That's one of the most expensive pigments. Underneath ultramarine, the red lakes come next. So having something that makes that red lake go a little farther makes a lot of sense. So we should probably keep this in mind when performing calculations to determine layer sequences. So organic red lakes, I made a number of them. These were the 4 red lakes that we made, and these are the elements I would expect to see with them. I said aluminum question mark because there's almost no aluminum added to make carmine, which is mostly a precipitation of the carminic acid. It's not even actually a lake in the truest sense of what we call lakes. So most of us here know what a red lake is, but just for those of us that don't, the simplest notion of a red lake, the most common red lake, so an aluminum mordanted red lake, is this idea of taking a simple chemical process. If we take alum, aluminum potassium sulfate, we mix it with an alkali like potassium carbonate or sodium carbonate, we will precipitate out aluminum hydroxide. If we do that in the presence of a dye stuff, so if this were cochineal dye in here, that cochineal dye would be coordinated on that aluminum hydroxide, and that's what we call lake. Just so, once again, we all know this, but it's called lake because that word comes from lac, which comes from shellac, which was one of the major sources of red lakes in the Middle Ages and the Renaissance. So just looking to the mordants, the aluminum, were we able to find that? Aluminum could be detected in 3 of the lakes, the Madder, the Cochineal, and the Lac Lake. And that makes some sense. That was actually a more major component. We could find tiny amounts in the carmine, but to the degree that it was actually almost difficult to know if it was noise or if it was the aluminum. Artex results without the helium purge here, we actually had pretty good results. The handheld, on the other hand, we could not see aluminum without the vacuum, which is why I was very interested in the last talk. Well, not the only reason. The XRF of mordants, aluminum once again. There was a minimal improvement in the difference in aluminum detected with the helium purge, just very minimal. If we look and see at the red here, this is with the helium purge. We are detecting more aluminum with the helium purge, but it's actually quite small. When you mix that red lake in with lead white, though, the situation completely changes. We're no longer really even able to see that aluminum anymore. So we can see right here the aluminum peak, which was visible before, is just a slight blip. That's when that lake was mixed with lead white. So I also had a red lake that I made with a calcium mordant. I shouldn't say it's just calcium, and actually there was alum involved in this as well. So you see the cochineal bugs here. They've been filtered out. This then filtered out. We have alum in here. We heat it up, add, in this instance, rather than the potassium carbonate or the sodium carbonate, I'm adding chalk. And we should end up with a mixture of calcium sulfates and aluminum salts at the end, which are going to coordinate with that cochineal. The calcium was readily detected in 3 of the red lakes, the cochineal, the carmine, and strangely rose madder. Well, there was no rose madder in my recipe. That really freaked me out. Where in the world did that come from? It could come from all sorts of places until I went back and reread Catherine Higgett's article in the National Gallery Technical Bulletin 26, when it says that madder is often grown in very calcium-rich soils and that there can be crystals of calcium right in the roots. So the next time I do this, I'm going to wash those roots really, really well before throwing them in there and extracting the madder. I didn't do that. So I would like to see the difference between the amount of calcium before and after, because we actually had a very high calcium account. Even more so than the cochineal, which actually had it in the recipe. So I'm not sure I've completely explained that. I'm going with that, though. The relative amount of calcium in the red lake was found to be quite small, and that would probably just relate to any calcium involved in just in that raw lac. The non-destructive detection of mordants can play a role in authentication as well. National Gallery Technical Bulletin recently reviewed their collection of Monticelli's, a 19th century French painter known to have inspired Vincent van Gogh. The tin mordanted red lake was found in all of his paintings, or almost all of them. And Kristen, who is here, found that on his still life over at the Phillips collection here in DC. I was talking about that a little earlier, so that's interesting. So we'll go on to can we find tin? Well, yes, we can easily detect tin in the pure metal samples, which have the tin component to them. Once again, though, the detection problems occurred when that was mixed with lead white, as tin and the K alpha can be overlapped by the lead L beta sum peak. And you can see here on that calibration curve where those fall. The relative amount of tin in the pure metal sample was found to be under 60 micrograms per centimeter squared. So from there, we'll move on to the ever-frustrating lapis lazuli, a pigment that often evades XRF detection, even when under a helium purge or vacuum. Again, there's the lingering question of whether concentration or even purity may play a role in successful detection of the pigment. There are many problems with the XRF analysis of ultramarine. Sodium, aluminum, silica, sulfur, all below potassium, therefore need the helium purge or the vacuum, at least most of the time. SI is in many, many, many things. And when it's mixed with lead white, which is very, very common, except in maybe the earliest, in the early Italian temper paintings on the Madonna's robe, it's often mixed with lead white, so we get the problem with the interference of the lines from the lead and the sulfur. We focused only on the aluminum. Yes, sulfur is an important component here, but also because of that problem with the lead and the sulfur, we focused on aluminum. I want to take this just a second to talk about lapis versus ultramarine. I teach historic painting techniques, and I'm very a stickler with my students about definitions of things. So there's lapis lazuli, which is the stone that traditionally was mined in Afghanistan, one mine up until the 19th century. When you grind that up, that's lapis lazuli. It has a lot of calcite and pyrite and other impurities in it. With those impurities, this is actually quite a beautiful sample. Normally, it's really a mid-gray. However, in the Middle Ages, the Arabs came up with an amazing technique to refine this pigment. It was put into wax. Chinino Chinini talks about this. We've probably all read it. But put it into wax with oils and balsams, let it sit for a while, then wrap it in linen and knead it under a weak solution of lye. Those lazurite particles are theoretically, well, Chinino doesn't say this, but theoretically more water-friendly. So they'll drift out into the water, and that calcite and that pyrite is more water-phobic, so it stays in that wax ball. So this would be done in basin after basin, starting out with the most rich of the ultramarines down to the point where you get really mainly impurities, and that's called ultramarine ash. So that's the terminology I'm going to use. And also, I'm going to try to compare ground up lapis lazuli versus ultramarine. Now, I've tried to make ultramarine, and it takes kilos of it to make grams of it, and so I've never gotten that far. So I actually went and bought the $15,000 a pound ultramarine, highest grade ultramarine from Kramer Pigments. Now, I used like that, but I did use that. We have the unrefined lapis containing significant calcium, iron, and surprisingly titanium. And I was unaware of this. It occurred in both of our samples. As compared to the unrefined ultramarine. We did see it in both samples, though. Aluminum was barely detectable using the helium purge and vacuum conditions. Analysis using the handheld alone was unable to find any aluminum in our research in the pure paint samples, though not even the ones that are mixed with lead white. There was a considerable suppression of the aluminum peaks when it mixed with lead white. This was also found to be an issue with the aluminum containing red lakes, as I mentioned before. So to that, I'm going to come to the summary. Really, we were able to find those traditional dryers, lead, manganese, cobalt, quite readily. Even in small amounts, those could be detected. Obviously, these should be considered when you're looking at an XRF and you're looking at analysis. I often wonder about this notion, or I'm now wondering about this notion of scanning XRF, and if we see areas of lead where we don't necessarily think of a lot of lead white or maybe lead chromate or Naples yellow or something like that. It would not be strange 19th century practice to take your McGilp and rub it over an area before going in and painting it in there with something that may not contain lead. It's called oiling out. We may see a lot of lead there. We should just keep this in mind. Aluminum, tin, and calcium mordants can be detected in red lakes. So the handheld didn't detect the aluminum unless it had that unless it had the vacuum attachment. The presence of lead hampered the aluminum and tin, as we've already said, and the calcium was readily detected. So once again, we should probably keep that in mind. And according to my work, alumina is very difficult to detect in pure lapis or ultramarine, more so than it was in the red lakes, and that there are a lot of impurities prevalent. And as I said before, the handheld in what we did could not detect it without the vacuum attachment. I'd love to try it with the instrument we just heard about. A lot of iron, calcium, and titanium impurities, more so found in the ground lapis, but surprisingly still some in that $15,000 a pound stuff. So really, I'm going to end it there. There are a number of people that we need to thank and acknowledge. We have Kelsey Mello, obviously Art Kaplan, and we couldn't have really done any of this without those thin film standards. Catherine Matson at Winter's Sral was there to help anytime that Jennifer Mass was not available. Some of the suppliers of some things. Kelsey Mell was an undergrad who did a lot of kind of really dry legwork with me making pigments and paints. And Kristen wanted me to specifically especially thank the scientists who organized the offering and offered the XRF boot camp at Yale. She highly recommends this to any of you who want to really understand the procedure and interpretation of X-ray fluorescence analysis. Thank you.
Thank you very much, Brian, for a very rich presentation. Are there questions? The organizer herself has a question. Annika.
I'm sorry to have all these questions, but I completely relate to this challenge of looking for tin in red lakes when lead is present, and this was something that we encountered in looking at some still life paintings, and I was really grasping at straws. Were you able to see some of the L lines, when you had the overlap of the tin K line with the lead L lines. Were you able to see the tin L lines to help with that at all?
Kristen helped out more with that. I mean, she did take the boot camp and was more comfortable doing some of that interpretation. I don't remember us really having a lot to grasp onto either. And I was there and we worked together, and I don't remember that. If I will ask her, and if she somehow had some magic bullet, I'll have her email you, but I don't think so.
Thank you.
Yeah.
Other questions? One in the back there.
One of my students, of course. Former students, anyway.
Hi, Brian.
Hi.
Gwen Manthe. I'm curious about the tube source, if perhaps changing the tube source for the XRF may actually excite the response from aluminum.
I would have to ask the audience. I'm not even going to try that one.
Perhaps the scientists might know.
Lisha will answer the question.
Right.
Well, you used a rhodium tube, right? That actually should have been good for exciting the aluminum because the L lines for rhodium should have helped enhance the aluminum. I'm surprised you didn't see it actually. Aluminum, that is, in your handheld?
In the handheld without the vacuum?
Yeah. Good question.
Well, we'll see. Jennifer, are you in the audience? This might be better.
I would have been more concerned because a lot of times there might be a little bit of aluminum actually in the instrument. I found
Sure.
with the handheld, and you have to be careful that you're not assuming that there's aluminum there and it's actually the instrument and
Right.
not an artifact as opposed to actually being there. So the fact that you didn't see it at all is, I'm surprised.
I think it was a matter of our vacuum, that we had been having some issues with our vacuum system. It was not as well as it was when the system, for example, was first purchased, so.
Oh,
I think we had a
Jennifer.
little leak going on.
We borrowed Villanova's vacuum for the second half of that, so I actually don't think that is the issue.
Okay.
I don't have an answer. I don't have an answer for that. We definitely did. I didn't talk about it, but one of the things that when we were at the Chemical Heritage Society in Philadelphia and could get no hit for aluminum at all, and we're thinking, this doesn't look anything like azurite, but we have a little bit of a copper hit, peak, and that turned out actually to come from the copper in the instrument. But the other way around, we didn't experience that.
Can I just follow up on the detector issue? Because I'm old enough to remember silly detectors. And the response curve of a silly detector was much better at higher KEVs. So you could see those L lines much better. And I think that was great for looking at things like metal points. So I'm interested in the new electronics in the cube, which I love, but if there was another cube we could put in to increase the sensitivity at the L lines for us, because some of those M lines are absorbed by the matrix. And so, I mean, even say cadmium, if you have a cadmium line that's next to, you know, an L line that's in with a lot of lead, it may be absorbed by the matrix, whereas the higher energy lines up top will come through. So just a plug for the don't throw the old-fashioned one out, is all I'm saying. Except you
Robert.
need liquid nitrogen, unfortunately.
There are lots of questions, which is great. So it prepares the floor for the panel discussion.
Hi, Kirsten Travers, Colonial Williamsburg Foundation. I was wondering if you had the chance to do any SEM EDS elemental mapping of the dried film, so you could see the elemental, like the distribution of the dryers within the film.
Right. Well, since this was about non-destructive, we stayed with that. Actually, we have plans of just punching out cross-sections and doing that at a later time. And actually, I'm having all of the pigments made. We have someone at the University of Delaware running XPS analysis on them to really find out what atomic number, you know, like what the percentage of each atom is in there. But it didn't seem germane to this, so we haven't done that yet.
Yeah, it'd be great to see those results.
Well, I think we can continue the discussion at the coffee break and thank our speakers for the morning, for their session.